All right, there we go. So what I wanted to do was set up a live stream here because I'm going to be 3D modeling the Leatherman Garage number 9 and wanted to kind of show this process to folks. So when the Leatherman ratchet came out basically a few years ago, I did my first live stream for that. So thought I'd give that a chance here. And what we're going to do, go ahead, open up the box. These stickers actually came outside the box, but of course I threw them in here for now. And then this is it, the Leatherman Garage number 9, otherwise called the adapter. And zoom in here. There we go. We have an instruction card here on how to use the ratchet driver, access the tools, using the T-shank holder. The only thing that's not really intuitive, of course, is the T-shank holder, and we'll show and talk about that. One thing that they did include was that the Garage number 9 comes with a Gridfinity holder. So this is 3D printed in what looks like PLA. One of the things even that I think they should have done with this holder was not add this little notch. Yeah, that makes this fit real nice, but it also means if you put it backwards, it doesn't go in right. It'd be nice if you could just put it in any direction. But still, nice that that's included instead of just the kind of typical blow molded or cardboard cutout that you end up throwing away anyways. So if you have a desk or drawer with Gridfinity, you always have a spot to keep this. All right, set that aside. Now, the Garage number 9 adapter by itself is a pretty cool little kit. I think anybody who's joining the stream is probably seeing a lot about it, and we'll talk about it. Howdy, Russell Thomas and CFM Tools, hello. If you're joining the stream, make sure and join on chat because I'm going to be checking in with questions and things, both to Leatherman Tools and the Garage number 9 itself. So to me, one of the things that people kind of forgot about the Garage series is that Leatherman made this to be an experiment. Even when they first announced it, that they were going to do all sorts of weird stuff. And this is definitely one of those tools. This is the first one without a blade. And to me, regardless of how you think of the utility of it or the overall quality or different pieces of it, it's really cool to see that somebody like Leatherman is experimenting with utilizing essentially 3D printing that is just kind of FDM 3D printing, but also this is the first time they're doing a metal 3D printed part. So this is 3D printed in titanium, and I don't think people realize how hard metal 3D printing is. It's not used heavily in the industry. It's most of the time the parts require post milling and more kind of post processing than you might expect. People sort of imagine everything 3D printing is the same as what they experience on the FDM printer, which is rip off the support, sand it a little bit, and you're done. With a metal print, there's going to be support structures that actually have to get cut off. So they have to strategically place those. And then there's also going to be typically some sort of finishing operations. The lowest cost, of course, is just tumbling the part, which is probably what they did here. Tumbling titanium is very difficult. I've tried making a titanium comb for the Free series and kind of ditched that because after days in a tumbler, the parts still weren't coming out smooth. And then the other things that are kind of experiments in here, of course, are the carrier, which is printed on, I believe it's PETG, a flexible plastic, which has the saw and file in there, the same saw and file that are in the Leatherman Mr. Crunch and also on the Surge. And then this is a flexible piece. These bits you can just basically pull right out, so you don't have to kind of slide the whole bit out. You can kind of just flex this and There are people who've had these that where layer lines are separating things. Mine seems to be in great quality. Yes, this is FDM printed, and it's not the, see, go focus camera, it's not the thinnest layer lines out there. But I'm imagining they had to print 1,500 of these with support material, and that's going to be a tricky thing. Howdy Russell, how do you get notifications on buying garage items? I was actually notified by one of my Discord members, so thank you for that. I get the notifications, of course, ahead of time from Leatherman, but because they are using Shopify and Shopify's email system, what ends up happening is that, because I use Shopify too, what ends up happening is that when you send out an email on Shopify, it will kind of parse those emails out over a long time, almost over the whole day. Even if you say, I want to send these out right now, their system doesn't email them all instantaneously. And that's kind of a problem for, of course, an instant notification. So they need to do some sort of other notification on a faster system. The emails are divvied out because just to stop spam filters and things where you can't send out 1,500 emails instantaneously. Is a solid holder not TPU? This might be TPU, might be, yeah, it might be TPU or PETG. I'm not sure. I'm actually, because I don't print FDM, I got a bamboo machine here, but I don't print it that much. I'm not experienced with exactly what material this is. It's obviously just something very flexy. I think that they did a good job of the overall design and making something compact. I do think that they could have done something a little bit better with the way it docks and the way it comes out. They specifically, you know, if you put this in sideways, it doesn't go in. Or you put it in that way, it doesn't go in. You got to get it rotated just right to go all the way in. I think they could have done something with the cap, maybe to pull it out. Make this so it's a looser fit. Put a magnet or something like that. So when you unthreaded it, it would be great if the cap just pulled the piece out with it. So do something to maybe do an insert inside here that allowed that, or you could thread this and then counter thread the inside and make a threaded piece here so that these guys pulled together. Something like that would have been great. Because this, to me, this garage tool, I'm going to switch over here, is kind of a juxtaposition of materials and things. We have an injection molded piece that's fairly complex and not cheap to make. And I'll talk about that as I go through the 3D model that I'm going to make. Combined with a stainless steel milled piece that is absolutely beautiful, obviously run on a very high-end machine, and then a 3D print and really quite kind of crunchy threads on the inside. I'm guessing that they had to post-thread this, that they didn't injection mold those threads in. They could have had a side action that does the threading, but they threaded it so deep in there, over almost an inch of thread, 3/4 of an inch of thread for less than half an inch of cap. Just seems like a weird decision. And then of course you got the pen and the micro screwdriver. Now these guys are FDM 3D printed, and I believe just out of PLA, because they definitely feel a little crunchy. And you can see the kind of bow out that happens. Darn camera keeps losing focus, sorry. Actually, let me do this. Let me zoom the camera so that I don't have to feel like I have to hold stuff closer. You can kind of see a little bow out that happens with the first few layers. And then the pen, which I don't think is going to last very long. It's not a sealed, pressurized pen. It is a very low-cost refill. Of course, that also means you can just get a low-cost refill anytime you need. All right, let me look at some questions here. PT doesn't reflect that in my experience, so I believe it's TPU. Yeah, I think you're right then. Like I said, I'm not, I print PLA 99% of the time as just a prototype. If I need something flexible, I'm using Tough 2000 resin on my Form 4, which is absolutely insane material. Or even the new Shore 80 flexible that is extremely stretchy. All right, now of course the last thing to talk about on this guy's the ratchet. And I have mixed feelings on the Leatherman ratchet. I love it, it's compact. I of course have side holders for it for all my tools. You can either do the new modular series or on my ARC holster, the Legacy holster. But I have a love-hate relationship with this guy. It's extremely compact, and it is one of the smallest ratchets. So for example, this is the one from Pipe Vise. That's small, and then there's the one, actually grab the right one for the Leatherman. And then there's the one for the from 711L. Now, if you haven't experienced the 711L one, it is insane. It is extremely tough. Feels like it can handle all the torque you ever could put through a 1/4-inch drive to a 1/4-inch output. And it probably can. They've probably tested it to that. But you can see it is so much bigger. It is much bigger. It is much heavier. My experience with the Pipe Vise is it's much, much cheaper feeling than the 711L, so I haven't really done anything with that. And then, but there's one flaw with the Leatherman ratchet, and that is the plastic piece here. So this is one that I've had fail, and I've only had one out of about 4 fail that I own. But internally, this design, pull it off of this guy. What they did is they put a spring in here that is pushing basically, or kind of retaining a ball, and then a stainless steel ball that actually makes the snap for the ratchet when you click this back and forth. And because this is plastic, eventually that's basically under constant tension all the time. And in fact, this is, I haven't changed the ratchet on this. You can see that mine is bowed out right here. It's kind of hard to see. Hopefully it's picking up on camera. But mine is physically bowed out compared to, let me grab the one that I just had. So this one's been on my belt for years. And this one is not bowed out. It's still a little bit crunchy and it hasn't cracked or anything, but eventually that might break on you and you end up having to replace the ratchet driver. So if they could replace this piece with something tougher, I don't think they're using glass reinforced nylon, or I don't even know what plastic they're using, and they're probably just using either ABS or nylon without glass reinforcement. At least it doesn't seem like it. With glass reinforcement, the texture is usually a little bit different in the shiny areas. So I think that they need to beef that up or replace that with metal, and then the ratchet would become an incredible product. But what we're going to end up doing is kind of going through this, 3D modeling it, and in CAD. So I'm going to switch over here. All right. Yeah, 711L is a boss. It is. And it's. I've actually started to kind of everyday carry it, even though it's bigger and heavier. It's almost half the weight of the Leatherman ratchet. So like here on my modular series holster, let's see, this guy's locked in right now. Let me grab this guy. You can kind of compare how big and how much space they take up. So it is more than almost twice the diameter, and probably about almost twice the weight, but twice the quality too. So, all right. So I'm going to start here in Solid Edge, and this is the Leatherman ratchet, my 3D model that I made. It's extremely accurate down to the logo. I did a live stream. This is my first live stream, was 3D modeling this guy, which is why I'm doing a live stream for the Garage 9, because it feels appropriate to kind of have these kind of bookended on each other. And we're going to start with this guy so we can use him as reference, obviously, so that we can make the 3D model of this guy very accurate and fit perfectly. So first of all, this CAD software is called Solid Edge. I'll explain a little bit of how it works as I go through. And we'll make a new assembly that includes this 3D model. And we'll stick with metric, even though a lot of it is going to be in inches. CFM Tools is asking, how do the pieces on your modular holster connect? So yeah, let me show you that just real quick. Let's switch over. So how all of them connect is a set screw. So you take a modular series, which is like the ARC holster here, And then there's the set screw there. There's a couple of detented spots. You can also just skip a spot if you, or just put it anywhere you want if you really want to. And then there's a dovetail action. So this slides into the dovetail. It's a little loose right now. And if I grab an Allen key, click that guy in, give this about 3 or 4 turns. And then now that's not going anywhere. This guy's magnetically retained. And then you can actually turn and completely lock him into place. Same thing with the Leatherman guy, it's exact same thing. And it kind of depends on the actions. So I'll be doing a video pretty soon on the modular series. There's some, like this is an upcoming version. The fun Tabasco holder that is upcoming, Baton 4. Those are all upcoming. All right, let's get back to the Garage 9 because that's what we're going to be doing about this. All right, switching over to CAD. All right, now how do you start with your dimensions on this if you're making a 3D model? I could 3D scan this. I do have a 3D scanner, but it's not really required for this. It's not a super organic shape. It's basically a double rounded shape with flats in the middle. They might have a very slight curve to them. I'll see that when I'm kind of getting into detail. And then the actual, because this is injection molded, there's kind of different rules that work around the way that part's designed anyways. So what we'll end up doing is starting with essentially the basic overall size, and we'll work our way from there. All right. Make me a little bit smaller here and the camera a little bit bigger. There we go. So first of all, how big is this? I can just measure this with calipers. So I'm getting 17.5. I measure a couple different places because this is injection molded. I don't know which way they actually drafted it. Up to 17.6, and then of course the metal piece at the end is 17.5. Now they also could have designed it in inches. They might be 6.9, but I'm going to do everything metric just to make it dead simple. And here's a cool thing that I can actually do with this is that because this closes and becomes tangent to this circle, basically I'm going to end up deciding that we're going to end up designing this guy first because these end up next to each other and everything will kind of build on top of that. So first of all, let's just take off the cap and let's start with the cap. So I'm getting somewhere between 17.5, 17.55. I'm just going to call it 17.5. Because there's knurling, it may end up being pushed out in a couple spots. So let's go with 17.5. So I'm going to make a new component. And I'm not going to care about where it is in the assembly yet. And we're going to put this into my server under Leatherman Garage 9 adapter, and we'll just call this 09 threaded end cap. Yeah, Russell, I got people who are ordering literally every single variant I have, I have one for the Fisher telescoping space pen, and I've had this on my store for about a dozen years. Hardly anybody orders them, and now of course everybody's ordering them for the modular, which means they also got to order the space pen. So hopefully they're using those Amazon affiliate links. Okay, here we go. I'm going to set this to metric. Oh, whoops. Why did that not save? Okay. Oh, I accidentally saved the assembly as under the wrong name. Ah, that's fine. I'll rename it later. And it's acting a little slow, probably because I'm streaming 2 different cameras out at once. All right. Oh, it says that live stream is experiencing issues, probably because of the CAD. All right, Let me know if it goes down. And we're not going to work around the adapter yet. So our 17.5. And I could also model this from the side profile and then revolve it. That would be the other way to do this, but I don't have to on this. 2.6, 2.6. And 12.72. It's probably 12.75, but it's been milled back a little bit in processing. So we'll go with 12.72. By a height of, let's go 7.6. Now I can tell by looking inside the cap here that they drafted this cut. It looks like it's drafted after it goes in a little bit, so I'm going to kind of guesstimate that by about 3 millimeters or 2.8 millimeters it's drafted on the inside. CFM Tools asking, does your end cap scrape the ratchet when you undo it while folded up? No, I think they did do a good job of not making it scratch. Oh, I say that and you can hear it. It does if I'm pushing on it. If I'm not pushing on it, it doesn't. I'm not really worried about it. I'm not the kind of person that keeps my tools perfectly pristine anyways. I'm always using them. All right, let's go with 10.8. On the inside. So we're going to pull that down 3. And then we're going to extrude the inside down an additional. So 6. But we're going to draft this. And I'm just going to be guesstimating. This is not critical. I'm going to guess that they did about a 5-degree draft. That looks kind of, to me, correct to what I'm seeing in reality here. And then there's a little chamfer on the inside. Can't tell the angle of that chamfer, so we're just going to assume 45 degrees. Maybe about a 0.4. Not much of a chamfer on the outside. There's a bigger chamfer on the inside. It actually does. Let's go ahead and do it at a 60-degree chamfer. Let me delete the sketches. I don't need these anymore. So the way Solid Edge works, the sketches are tools to kind of build up what you're working on, but you don't have to keep them. Not when I'm in synchronous mode. Makes it very fast. So we're going to go with an unequal setback from here of 0.4 to the outside and a 60-degree chamfer. It's actually going the wrong way, so let's go with a 1. It's not quite that aggressive. Whoops, too much. That looks a little closer to what I'm seeing here. Now, of course, they're going to chamfer the edges here before they go and knurl them. Let's make them about 0.4. Now I forgot to bring my magnifier out here. So some of this I'm actually going to be almost using the camera to see. Yeah, I might have to go get my magnifier in a minute here. All right. Howdy. NKMSVWDE. I don't know how to pronounce that. You're the man, excellent customer service. Snapped a piece off of one of my sheets and you had a new one out to me by the weekend. Great guy. Thank you. Thank you very much. All right. And just to complete it so that it looks perfect, we'll go ahead and put a tiny chamfer on this edge. And we're going to set this up to be made out of stainless steel. This actually sets both the color and the actual physical properties, so I can actually simulate this and determine the weight. And now the chamfer on here is a straight cut. And I might need to go grab a magnifier in order to really look at this in detail. So bear with me for just 1 second. I'll actually still be on mic as I run across my house. Okay. Now for the goofy magnifier look. Is that good enough for you? This is a godsend when you get my age. All right. What I'm looking at here is trying to figure out the angle, essentially. And it almost looks like it's a pretty wide angle cut. I'm guessing it's a 60-degree cut. So in CAD, what we'll do here, and now I'm actually going to switch over to ordered mode. So ordered mode is more like traditional CAD where everything's based on a sketch and has a history. And we will go with a polygon. Actually, no, we'll start with just a little line. Starting on this plane. And we're just going to kind of guesstimate how far in that chamfer is. Maybe 0.25 millimeters. Like I said, it's fairly wide chamfer. And so I just need to cut this away. And to make it look correct, I'm going to radius the inside by about 0.2. This is more geometry than you need in order to make a product, but when I'm kind of making something that looks photoreal, I want to do it that way. All right, so we're going to extrude based on that sketch. Just that cutaway, don't need the sketch anymore. And then we're going to pattern that in a circle. Locked here. And we're going to guesstimate these. I could get in there in detail and count. Looking at the actual part, there is a small flat, about that big, so probably somewhere in the neighborhood of 48. This looks right. And then we're going to work on the threads next. All right, so for threads, what we're going to end up doing is a sketch that's going to kind of define these. So unfortunately, I do not have a thread pitch gauge here at home. I have one at work where you could just push it up against the edge and kind of compare it. So we're going to have to look at this with the magnifier. All right. So what I'm going to do is measure between. Usually you want to kind of measure 3 or 4 threads and do some math in order to kind of kill the average, but there is only essentially 3 threads on this part. And what I'm measuring here is basically just between the threads. And they could have used an inch size, they could have used a metric size. We'll kind of figure that out. Actually, let's figure out what the outer pitch is first. And it's 14. So they probably used a metric M14 thread. I'm actually surprised they used a machine thread for this instead of a little bit more coarser plastic thread, plastic compatible thread, so that they could not have those threads get torn up. And it looks like it's M14 by 1. So that'll make it easy because that's a nice standard. All right. And I got to figure out where these threads are going to start. So if you look at the part here, there's a little kind of raised area where it comes up. I wish I had my other camera so I could actually zoom in a little bit better here without losing focus. But there's, of course, there's a 45-degree chamfer. It comes up. That's where they eat the threads away when they machine it, and then it comes back down. And so essentially this surface and this surface are typically the same diameter. I guess I didn't double check if they actually are. They don't have to be. 12.69. So essentially 12.7, or so they basically are the same. If it's slightly smaller, it's probably just while their machine it deviated a little bit. So we're going to come up and grab the magnifier so I can see this. The start of that 45, I'm getting 2.4. Let's double check a couple spots. Looks like 2.3. So I'm going to come up 2.3, 90 degrees, and I'm going to come over to the edge, and I'm going to come up 45, and then I need to go where the ends of the threads are. Let's come back down here. So measuring from the base, so there is, it's like 5.3. Come out to the part, come off 45 degrees, and then we'll come out 14, or actually 7. And this is the area where the threads are. And so it's going to be the area we end up cutting away from later. So for now, we're actually going to revolve add this. So we're going to erase all these other pieces, leaving us just that. And I can close the sketch. And I can do a revolve operation on that sketch. And let's see, oh, second, in ordered mode, I need to set an axis first. So I've got to jump back into that sketch. Why won't it let me do an axis first? I guess I can't. Okay. I don't use ordered mode all that much. In fact, what we're going to do is, let's go ahead and switch over the whole design over to synchronous. Because it's so much simpler to do these operations. Grab that, by that, and 360 degrees. All right. And there's a couple ways I can do the thread on here. There's actually a thread operation in the software, or I can kind of manually draw it. So we're actually going to use the thread operation in the software by adding a new body. What we're going to do this as a cutaway. Essentially, we're going to make a tool. And so this tool is going to be essentially building a virtual tap. So what we'll do is make something that's about 16 millimeters on the outside, 14 millimeters on the inside, a cylinder. It just has to be long enough to cover that piece, so up by about 6. And then we're going to hide the other body for now, and we're going to use the thread operation in here to create physical threads. Now actually, for this to work, I can't be in an assembly. So I'm going to have to close for a second, open this part separately so I'm not in assembly mode at the same time. Just some weird limitation where the physical thread operation doesn't work in assembly mode. All right. So go by thread, options. And this is why, since it's a nice standard, we can just find M14 in my chart here, M14 by 1 millimeter pitch for the entire cylinder. And we're going to call it a physical thread. It's going to warn me that, you know, typically you don't do these kind of things in CAD, you just do it virtually. But my CAD software is fast enough that it can actually handle all this without any issues at all. And then we'll do it just a subtract operation. We're actually going to do that in ordered mode. So if we need to change the thread for some reason, we can. So in ordered mode, we'll go back to subtraction and we'll subtract our tool. Switch back to our design body. Delete the sketches we don't need. And we're also going to repaint the part because it's added some thread looking pieces we don't need. Come on. There it goes. And voila, now we have the cap done. So this should be pretty darn accurate. I could now use this if I wanted to make an accessory that threaded in. All right, and we'll save that. Switch back over to our assembly. All right. Now in the assembly, we have the ratchet and the cap side by side here. And like I said, they're tangent to each other. So that's going to be very helpful for kind of building the rest of the assembly. So we get everything concentric to these two spots. And so I think what we'll end up doing is go ahead and assemble it this way, and then we'll kind of build the rest of the pieces upon that. And what I want to do is associate it though so that the center of the assembly is still the center line of the part here. Although it's actually not, I guess it's actually not even now that I'm looking at it. No, it's not even, so we won't worry about where they're positioned relative to the axis. We won't care. So we got the ratchet grounded, meaning it's our primary component, and we're going to associate stuff off of it. So I'm going to make sure that this face and this face are even. They are, when the cap is threaded fully, those are pretty darn even with each other. Enough that I think I can build the rest of the assembly. Might be a tiny bit of difference, but I think if you could get the cap threaded 100%, it would. So that was the design intent. And then I want to make sure that the coordinate system of the part is even with the coordinate system of our assembly. It didn't look like it did anything there, but actually those two are already on top of each other. So now if I drag this part, he's kind of locked. He can only go in one axis. And then we will end up making our outer surface tangent to this guy. So now they're touching. So that'll let us build kind of the rest of the geometry of the part. I could measure each individual part and then assemble them after the fact. And we'll do that with a couple of the pieces. But this way, it kind of gives us reference for exactly where all the different components are in relation to each other. All right, save that. And we're going to go ahead, I think we're going to move the axis of our new component because I'm going to leave it, we're going to move everything over so that the ratchet's offset instead. Because this plastic piece is kind of the main component that we're going to build everything around. And then we'll get around to the titanium 3D printed piece later. So what we're going to end up doing is taking this guy apart. So let's unthread the cap. We'll use our little bin here to hold all the other pieces. Now I already have 3D models made for the Leatherman bits and for the saw and file, so I won't have to make those. The pen will be something pretty easy. Those are actually a standard. It's actually ISO standards for those. And I don't have enough fingernails to pull these guys out. And I got a 3D model for the microbit driver already too. So we won't worry about those till later. But let's go ahead and take this apart. Now, this is the first time, I think, at least since the free series, that Leatherman's included the tool you need to service the tool you have. So let's go ahead and use our arc. Of course, you can't service itself because you can't use the driver itself. Uh-oh, why aren't you going in? There you go. And I think they used at least a variant, or they used the free series for these pivots. We'll see. I haven't taken this apart yet. Let me get this into a little more zoomed in mode here for now. So there's some blue thread locker on there. And I'm willing to bet this is the same as a free series pivot screw. Why don't we figure out if that's true? Nope, not the same as a free series pivot screw. In fact, this might just be a regular off-the-shelf Torx screw. Now I really need my thread gauges. I don't have my thread gauges for figuring out if this guy is number 256 or if he's like the ones on the pivots on the free series I think are like 248. They're a little bit odd. I'm hoping they use this regular screw, so we'll push this guy out. If I can get the pivot out. Let me get something a little stronger to push on that with. Grab an Allen key. I don't want to tear up the threads. There we go. Come on. So the shoulder screw there, it's definitely custom. So I'm guessing they obviously got the hardware to make their own Chicago screws for the Free Series and other tools. So it's still probably a custom screw, but they might have used standard heads. We'll get to those screws in a little bit. All right, we'll pull this apart. Get our first look at the 3D printed titanium piece. Pull this screw out. And the ratchet. So the 3D printed titanium, you'll end up feeling on the inside that the surface is rough. You basically use this little chunk as a nail file. Mine's labeled 285, 289. I guess I got my magnifier. I should go look. 285. And when they tumble this, a lot of times the tumbler does not get into any of the internal surfaces. Probably because they're using very large ceramic triangles, essentially pyramids. And that is also why that surface in there is not getting smooth. And I have, lots of people have complained that that surface tears up the plastic, and while it will scratch it the first time, once that pattern is kind of etched in, it will probably actually settle out, and I don't think it'll actually continue wearing, because once all the grooves are in, they're all going to kind of distribute the pressure. But if you need to, you could get in there with a nail file, and maybe we'll do that in a little bit. But I'm not ready to 3D model this piece yet. We're going to 3D model the plastic injection molded piece. And this is going to be a little bit tricky. We're going to go ahead and thread in. Well, actually, no, we know this is 2.6, so we don't need that. This guy's going to be a little bit tricky to 3D model. There's some geometry in here that's kind of derived off of the ratchet, which fortunately we have. We're not going to worry about the pen cutouts till later. And I'm just kind of studying this to figure out where did they... Obviously, the gate, or the ejection ports, which are these circles, these smaller circles here. So they obviously injection mold this, push it out of the tool away from those pins. That's where the push pins that pop out the plastic tool are. In order to do these guys, they have to do side actions. And then, of course, the interior is in its side action all of its own. And let's grab a flashlight, take a look inside here. It is very smooth inside. It has to be in order for that gate action to pull that out. It's completely sealed. There's no spots where it goes through. So there's no places where they have mating faces between side actions or anything like that. So that's very interesting. And then there's I can see a little bit of a bump out on the inside on one side, where behind here. And then, of course, it tapers in around this piece on the inside. And we'll worry about the insides later. So let's get started on the outside. All right. We're going to make another new component. What's not new? Create a new component in place. And we'll leave it at the axis of the assembly for now. And we'll just call this the 009 handle body. Oh, sorry, I did not switch my camera back over. Did not mean to do that. All right. So as far as the diameter of this guy, oh, actually here, I can see the seam. The seam runs right along this edge. And it's interesting that I don't see, they must have to tumble this. There's a tiniest seam right here. Let's see if I can exaggerate it with a flashlight. Yeah, there's a seam on both sides. In fact, there's a textural difference right on this edge. So there's multiple actions that have to make this part. So they may end up literally having an action here, here, and here, 4 sides coming apart, making this very complex injection molded component. The reason why I didn't think that like the seam here was the only seam was that this actually looks like it tapers back down on this side. So it's not flat on this, it's curved, and then starting at that seam, there's another curve going that way. So it's going to be a little bit tricky to get this to an absolute perfect 3D model. Your first inclination is going to just assume that that's flat, but it's not. So what I need to do is find maybe the thickest part of this, and what I'm trying to do is apply as little pressure on here as possible. But if I'm getting 17.5, that makes sense. That's the diameter of the head here. So let's go with 17.5 is our starting point. And let's take a look, putting the parts back together, and kind of how these guys interact. So I'm trying to figure out the design intent of the person who designed it in the first place. With a 3D print, they can do any geometry they want. There's no such thing as the tapers getting in the way or anything like that. And I can see on this face, even though that looks like it would have been a flat, it's actually thicker on this edge than that edge, so that is tapered. So this is going to be a tricky guy to figure out where's the middle, exact middle. I think the exact middle is actually where the pens are. Let's try to guesstimate that. So if we have an overall thickness width, trying not to compress it too much, 30.2. This is going to have to require a little bit of guesstimation. Trying to figure out where the center of that pen might be to the outside edge. A little bit tricky to figure out. I'm having to kind of go off of the way the light plays in order to find the center of that. Somewhere in the neighborhood of 15, so that's not exactly centered. Yeah, this guy's a little bit tricky. All right, let's try to build the overall profile and then start cutting away the areas. So I'm going to guess what they did was they got essentially the diameter of the 17.5 of the cap, and then the diameter of the ratchet itself. And that's what this part is. This part is essentially the same diameter of the ratchet itself, which is just that piece here. Although there's a very slight taper there, and then it expands. So it's a little bit bigger than the ratchet itself. It's a tricky thing to try to figure out here. Because that expands outward. Now that one almost looks like there's flats. Sorry. This is what you end up having to do when you're trying to figure out something organically. This guy might actually be better off with a 3D scanner, but we'll skip it for today. So if that's 17.5, then, and it tapers down, that means that this cylinder at this end can't be the 17.5, which it is definitely smaller, probably intentionally so that you can get your fingers on the knurling. I'll have to decide how precise I'm going to be. I'll try to figure out maybe 16.6 or 16.5. Let's go 16.5 on that end. And the other end, it might come down to, depends on which end I want to do this. Because this looks like they made a symmetrical part that they kind of cut away from itself. And because this continues as an arc over that edge. And the thickest part, like I said, is 17.5 down to 16.5. So let's assume they made both sides symmetrical. with it being 17.5 in the middle. So to get the middle, we'll go here, and we'll come out 17.5. Now, I don't think they used an ellipse. I think they just used a bigger circle. So we just need a tangent circle here that is tangent to those guys. And we'll mirror this across there. Subtract all the insides and the outsides, and that's kind of going to be our core shape. Why did the bottom not become tangent? Something's wrong here. I probably just screwed up all my numbers. 16.5, 16.5, and let's double check that he's aligned to there. That's probably what happened. And the distance between these, come on, give me that spot. Call it 14. Don't think that's actually right. Let's do this. Let's go back. Let's delete that. Let's go ahead and just make him concentric to our existing ratchet. All right. Just need that as a reference. Okay. Now the numbers are kind of, they are whatever they are, but I think our diameters are correct on the outside. Don't need these guys. Okay, that's our 2D profile for this shape. And because they did what looks like multiple side actions on 4 sides, that means they didn't have to taper this all the way down. If it was injection molded, which you wouldn't do it long ways anyways. So that means they could keep the same profile the whole way, which I believe they did. So let's go ahead and come out to, let's call it 89.7. All right. Second here. All right. Next feature I think I want to have, just because it's sort of a point of reference, is this little angle on here. And that'll kind of keep my brain oriented a little bit. So what I'm going to do is measure, well, one, I kind of know the diameter of this because when it's docked, it matches up with the 3D printed piece here. And then that 3D printed piece, still trying to decide if it tapers down at the last second. I think it does. So it's a little bit bigger, or I can just try to measure it, but let's see what we get here. $14.9, but I don't think that's the actual center of it. I have to kind of figure out, where does this circle end and where does the taper begin? It's a little tricky to do in order to figure out the radius. Let's go with the 16.4 we had earlier. All right, so from the center here, 16.4. Let's see. No, it's not going to be from the center there. Darn it, can't figure that out right this second. Well, sorry. This is the part of CAD of just staring and spinning, but this time I'm doing it in reality. Trying to make sure, are these circles actually completely in line with each other. I think they are. So there's no way that that is 16.4. Because it has to start there. It can't even be 15. What's going on here? Second, let me try to figure this out. The other way you can do it is to just come down from the edge, trying to guesstimate what that's going to be by putting down a straight edge, measuring this gap. .5. All right, as far as the angle of this, there's a couple different ways I can measure it with a protractor. The other way to measure it is to actually kind of hold up the part here while looking at CAD and visually just aligning it such that the part is the correct scale, and then you can actually get the angle pretty accurate. And this did snap to 75 degrees, looks about right. I can always adjust this later if I need to. And we're gonna do this as a revolve operation. It's gonna be a little bit harder to do because of that extra taper. Let's see how it ends up working out. I'm gonna revolve it as a cutaway along that axis. See, the problem is it can't just keep going. This is a little bit tricky. Some weird geometry going on here in a couple different spots. There's a little bit of a sink there, but that could just be from the injection molding. The other way to do this is a cutaway that is tapered after the fact. That might be the way I have to do this. So from this face, make a circle like that. And we'll just leave it with flat edges on the, for now. Not the best way to do this. It doesn't matter how far I cut this back for the moment, because we're going to use the draft operation to draft that. And it doesn't like it. Why does it not want to draft that by the 15 degrees? Should be able to do that. Let me think about this for a second. The other way is to cut this back with a 15-degree angle. Like that, but then these edges aren't matching up correctly because of the way they did this. Sorry. I thought this was going to be a simple little component. So those aren't just going to disappear. And I don't think the radius here is correct. So this actually might be a two-part loft operation that is actually ends up looking like a chamfer from the side, but it's not, because it's actually a different radius here. And then it's actually projected to a kind of a curve that was projected down from one axis or another. So we won't worry about that for this moment. All right. Dylan, P2U. I'm so happy you got your hands on this. Thank you. I do plan on making some accessories. I guess you could talk about those. There's already a couple that I've seen people do with 3D prints. Obviously, I think this guy might be able to be improved upon. Maybe a little bit better fit. I would like to see something where like I said, where the cap pulls the insert with it so that you can pull that out, use it, and put it right back. The hard part there is because of the flats at the bottom, you can't have something that spins as it goes in. So it almost might be like magnetically coupled or something. We'll have to figure that out. All right. I'm obviously getting nowhere with that little feature. I will figure that out later. So for now, let's just try to do some of the other features. So what we're going to do is come down and just figure out this overall thickness. And because they use 4 side actions, this shouldn't be tapered. So let's go 16.6. And I don't care where this line starts or ends at the moment. And then the overall thickness of the longer area here, 22.1. And then obviously there's a cut between these two at an angle, and there's a cut back here at an angle. This one is a little bit tricky again. It is an angle that has been swept out. So let's start from, come on, give me the cross point. Let's go from here. And this is going to be guesstimating because there is a round on that edge. I have to kind of just figure out where that virtually is. Come on, get the calipers in the right spot here. Somewhere in the neighborhood of 5.8. And then again, I'm going to hold this up to the screen and figure out what that angle is. It's more than 45, so let's try. Let's try. Almost a 40-degree angle. And it's actually, I think, revolved around the axis of this guy. So go to the revolve tool first. And I just need that one face revolved around that axis. Let's see if this looks correct when I do the cutaway. It doesn't quite go all the way around like that, so I might have the angle wrong, the start point wrong, or again, this might have been a lofted operation and not a revolved operation. Let's play with a couple other things first. Let's try to finish this 2D profile. And in some ways, when you're trying to do this, you can see how many times I'm like changing what I'm doing. And a lot of times that's because it just simply doesn't look right. So I can't tell if what mechanical operation they used in their CAD to get these. Okay, so I'm measuring from the end of the part here, trying to find the virtual endpoint, which is hard. We got to basically find the center of that curved section in order to figure out where that ends. So end somewhere around there. Let's go with 34.8. And this angle looks like a fixed, looks like it's 45, but let's take a look at it. Comparing the part to the CAD. Yeah, that's a 45 or a 50, you can't tell. Let's try. Yeah, it's closer to 50. All right. Let's trim this up a little bit. We don't need that, don't need that, don't need that. And we won't worry about that one for now. And then there's obviously curves to these, but we'll add those curves later. And I just need to cut this away in order to make the main profile. Now, what I'm also going to do again is comparing this by looking at the part compared to the screen and just seeing if the overall outline. So what I'm doing is I'm visually matching up the total length of the part because that's going to get me the most accurate size, and then just kind of visually looking at the edges and seeing if I can basically cover the CAD model with the real part, and you'll see if there's spots where you're off like a few millimeters or your angles are off. And I think we're good. And I think this guy's angle is wrong. And so what I think I need to do is actually go back to this face and go ahead and give us a circle like that. And then this actually needs to start from there. Let me, or does it start further back? No, it does start from there. Okay. And let's go back to -140. Now we'll revolve this, and it won't get into cutting away, which is what it was doing earlier. That looks much more correct to what we're seeing here. There's some rounding and other stuff going on, but we'll do that later. Don't need these sketches for the moment. All right, save. Even though I'm not going to cut away the inside yet, I'm going to give myself the start of that. And there's a certain chunk of this that doesn't have threads anyways. So 13.6. And we'll cut in by... No, actually there is threads immediately. Never mind. Okay. How deep are those threads? I'm gonna have to guesstimate this. Need a flashlight. $19mm of threads. Let's say that they try to thread it to 20, which is a ridiculous depth to thread a plastic part that only has a 6mm part interface to it. So they might have used an off-the-shelf action that did that. I don't get, because that means that the side action, when they injection mold this, that side action has to unscrew 20mm of depth in order to clear the part, along with the actual insert. So how did they do that? Because the insert doesn't have a round at the base. I'm curious how they injection mold that. So they probably post-milled this then. Because otherwise, that would be ridiculous to have a side action that did that. All right, I'm going to catch up with chat here, sorry. Dylan P2U, are you able to sell these through your website? The Garage 9 is a limited edition. I'm not able to sell them. I've tried to sign up to be a Leatherman reseller at one point, but even then, it wouldn't be the Garage 9. So a limited run garage item? Absolutely not. Yeah, that's exactly what he said. All right, let's continue. I'll worry about the threading there later. And I think just because it's going to kind of help guide some of the rest of this, let's kind of figure out where these pen inserts are. So there's a certain amount of thickness they had to leave. And then the pens have a certain amount of diameter. So I'm actually going to start at this end measuring, because these to me are derived off of where these landed. With an injection molded part, you have to leave certain thicknesses and things in order for stuff to not sink. So I can kind of measure this. So they either left 1.5 or 1/16, which is 1.6 of a material behind. It's a little hard to measure this. Let's see here. Yeah, that's tricky. See, the 1.4, I can squeeze it to 1.3. It's a little bit of a soft plastic, so it's kind of too easy to squeeze. I'm going to go with 1.4. So 1.4 from the sidewalls. And I'm just going to give myself some reference lines here. Don't care where they are. 1.4 in. And they're going to be symmetric on each side, so we're only going to build one. It is a little bit different, the pen depth from the other piece. We'll worry about that later. And then the thickness of these channels. Looks like maybe 2mm. Getting 1.9 to 2. It might be 2 tapered in a little bit, so we'll assume 2. And that's now going to give us where these guys kind of land. And then the next thing we need to figure out is where do they belong this way? And again, I think they're going to be derived from this end. So if I grab the pen, Well, the pen has a diameter of 2.3, so that slot can't be 2. Why am I... So... Well, these had to be side actions, meaning they had to have a tool come in, provide that void, so they could have, with their tooling, actually made this so that it's not a cutout coming all the way up, meaning it's an actual half moon, half circle here, which would make some sense. So that's even trickier. That means that what is left exposed is measuring as 1.9 or 2, but the channel inside is probably 2.5 or even 2.6. Could be 2.4 to be barely big enough for the pen. See how this feels. It goes in pretty loose. It does tighten up at the very end. Now I'm going to assume that what they did is they tightened up this piece at the very end and not the pen itself. Actually, we can test that because the pen comes out. Yeah, so the pen is completely loose. So that means that this is not tapered here. This is probably tapered at the very end in order to get that feature. Or, actually, this piece is probably tapered. Now, because it's a side action, they still have to kind of taper it, but they taper it by a very, very small margin. All right, let me think about this for a second. So that means this guy is probably 2.4 or 2.5 on the inside with an exposure of 2. So we can kind of still do that from here by looking at this face, making ourselves a 2.4 circle. All right, give me the dimension so it's locked. There we go. And I'm going to project this line over here into my sketch, and I'm going to make sure that the circle touches those. Whoops, second, that line needs to be locked. There we go. So what this will end up doing is leaving that little bit of edge exposed by the time it cuts down to that depth. And I got my watch is magnetically grabbing crap. All right. And worry about mirroring this later. So we're going to extrude that circle to a depth. So you can see here that it's leaving the resulting cutout that ends up being 2 millimeters wide at the end. And let's figure out what our total depth of this cutout is. .72 millimeters. All right, again, I don't need the sketches anymore. Yeah, that's a little tricky. Now we can also do the other cutout because now we know exactly where this circle ends. And this guy has at least a starting diameter. It's, like I said, it's probably tapered because it's an injection molded piece. So it starts maybe 4.4. Let's say it starts at 4.5 and tapers down. And it goes in a depth. Also, that's actually interesting because it's not doing the cutaway here. So there's a couple ways they could have done that cutaway, but I think the circle does intersect with it. So what did I get wrong? Either the overall height of this is wrong, or the actual position of this is wrong. Tricky. Plan is to sell these for $20 with no ratchet, right? Howdy, Studley. I'm not going to... Yes, I'm doing a 3D model so I can make accessories. No, I'm not going to be 3D printing and selling just these handles. All right, something's wrong here. 17.5. Let's double check that I made that 17.5 at a 90 degree So my thickness there is correct. So position of this is wrong, or the diameter of this is wrong, or they did something like this pen cutaway comes up and has something like this that finishes the actual cutaway. So I'm gonna get with the magnifier and let's take a look at this really close. So there is a radius, and that actually might be all that it is. So in which case, I grab this face and this face. I don't need these guys. And there's a radius here that's doing that opening. And let's try to get this correct by giving us a guideline by how wide is this opening measure. So physical openings, 3.34. Let's go at the top, 3.5. Let's just call it 3.5. So that's how big the opening is to the outside. That makes a fairly big radius of 0.6. I don't think it's actually that big. It doesn't look that big. So we're going to split the difference, go 0.5, just to get this continued moving. Like I said, this is going to be to design accessories, not verbatim still Leatherman's IP. So the reality is I actually don't need it to be that accurate. I just need it to actually be correct on the outside for now. I just have a problem with always making things that accurate. All right. The catch is we won't be able to taper this properly, but we won't worry about it for now. It'll still look pretty damn good. This measures a depth of 30.6. There's a little glitch at the end and some other pieces, but I think that has to do more with the side actions than with the actual design of the part. All right, save, and this looks good. So Studley's asking, I assume, about accessories to go with this. Yeah, so I'm thinking about obviously maybe a replacement to this guy. It may end up being SLA 3D printed and something flexible in order to emulate some of the way this works. Or it could be SLS 3D printed, but what I'm going to try to do is get, it's going to be, I can't really measure this, but what I'm going to can do is kind of experimentally figure out what's going to fit in there. But I think something so that the accessories come out with the cap would be good. So it might end up being putting a big magnet on here or something. I think that the overall design of this is actually ripe for adding other stuff, like adding something that completes the other half, that docks in and then completes the other half. And I saw somebody on Reddit already, and I'm going to steal his idea. He used the T-shank to actually lock in a bit holder, so similar to this guy that I'm designing. But he did it for 4mm bits. He kind of made a wraparound piece. It was too big. I think it could be tighter fit. All right. Tega Tech will be making these files available for use. I will be making some of the accessories available to use. I will not be making the CAD files of the actual tool available to use. My CAD files, you can see how much detail I put into them. I consider them the same as reverse engineering Leatherman's IP, and I don't need to share that with other people. I like Leatherman. They keep me in business. Are you in VC Zap? Mind if I join? No, I'm not in Discord. Just on live on the chat here. All right. Next up, let's go ahead and mirror this operation. And I'm not going to make it exactly the same. Don't need it to persist. I do need it to give me the right face. Why is it not giving me the base face? There it goes. And like I said, these are slightly different depth. So that one was 72. We'll adjust the depth of this guy. And I want to make sure I don't accidentally adjust the other one on the other side. And let's measure this. So I guess just 70.2. And I already told you not to do symmetric software. 1 second. Break the mirror operation. Why did it persist? It didn't say it persisted. Come on. I'm getting some weird behavior right now where it does not want to turn off. It doesn't want to let me interact with this window. Should be able to turn all these features off at once. That's what's screwing up. I think the streaming slows down the software and just gets laggy. All right. I think the next operation I want to do is figure out this piece here, because some of the other pieces are kind of derived off of it. So they have an offset from this side and an offset from this side that is uneven. And so for this side, I can kind of measure the thickest portion of that, and that'll get me that distance. It's like 2.5. And for now, I'm just going to give myself some reference lines. I don't necessarily need them yet. And from this side, can't really measure the thickest part because it basically disappears where that is. So this one I have to directly measure off the top edge here. I got to find the thickest part. Looks like 6.8. Or actually I could go from the one I'm more confident about, which is a 2.5, and come up the thickness of 8. All right, that's what I'll do. So that just gives me a reference line for kind of where that is. And we're going to give ourselves a plane that starts at that edge of that line in order to build off of. Now, where the location of this hole is, I can basically almost visually tell, but I think it's at the intersection of these two pieces. Yep. Which of course makes sense. That's where you would put it, but sometimes things can be offset in weird ways. Now, the diameter of this is like 12.5. All right. Take this magnifier off for the moment until I need to really look at something in detail. All right, now, even though I measured this 12.5, that inside edge is probably not 12.5 because you need a little bit of tolerance for this to spin on, essentially. So I'm just going to guesstimate 0.2 or 0.3. Let's go with 0.2. It looks pretty tight. So I'm doing an offset of 0.2, and that's what we'll make for our cutout going up. And I'm not going to worry about tapering it until later. And now we can come down 8. And on this operation, the exact same thing. So from this face, we'll do the line that gives us our 0.2 offset. Whoops, I don't want the face, I want the edge. I'm going to catch up with Chet here. What do you think of the print quality of the sled? I saw a lot of complaints, but I do not think it's that horrible. Yeah, I don't think it was that horrible. Mine is pretty good. Yes, the layer lines are thick, but this is also like they had to rapidly produce 1,500 of these. And I mean, mine feels really robust. It's extremely stretchy, bendy, and nothing's coming apart. So it's doing the job. Layer lines look good as far as on the inside, and I didn't have any burrs or anything. So I think they did a good job with it, considering how many they had to make, and considering the geometry of this part. Because the layer line, or because you can see the part this way, my guess, oh, I'm gonna have to turn my camera or lights back on in a second. And I can see cross hatching this way. So that means they printed it down just like this. So this is the bed with some supports, which they probably use like PLA or something, so a dual operation. And then the layer lines kind of build up on this edge. So I think that's why these guys look rougher, is that they're actually kind of overhung and sitting on a support structure. But I still think they did a good job with it overall. All right. Alexa, turn on the workshop light. There we go. Switch back to CAD here. Nick Fowles making his own tool tray and a 5/32 bit kit. Like a 4mm bit kit, you mean? It's kind of weird. They've got 1/4 inch and then we got 4mm, but yeah. And then also work on another mod as well. Yep. And I might be able to release like an exterior version of this model. That might be a possibility, but typically I don't like to share the models in detail. All right, so this guy's got a radius on this inside edge here, and that's not something I can measure directly. Well, actually I could. Again, I'll be right back. I gotta go get my radius gauges. Again, due to the joy of wireless mics, I should still be there. Things I forgot to bring before I started this. All right. So these are my 3D printed radius gauges. Need the inside radius. Now already pretty close with 6. Could even be 5. There's a gap. So let's take a closer look. 6, I can't find any gap. 5, there's a hair gap. So we'll call it 6. All right. That's real easy to do here. Just call that 6. Now it's going to do this weird piece there, which I don't want it to do. I don't want it to continue on. Yeah, it's annoying. Fortunately, the simplest way to fix that's just going to be to cut it away. Doesn't matter. And I need this face, or this edge, to complete the shape. There's a shape in there. All I have to do is get it selected, which, the way this CAD software works, you kind of mouse hover over something and it will then let you select when there's multiple objects. So I cut that away. And then back up here. Actually, there we go. Actually, I don't even need to do all of the work I just did. All I actually need is that edge, because I just want that edge to go straight. The other really awesome thing is I can do stuff like this with just one edge, making an operation. And like I said, sketches are tools to get you geometry. After that, your geometry just lives by itself. Like, I don't need that plane anymore. In any other CAD software, I deleted that plane and it would just break because all the associations would be gone. All right, now that we have some of this geometry, let's see what we're going to do next. There's a little cutout right here and another one down here. And this one up here is where the T-shank interfaces. And I'm kind of curious why it's got this L, kind of rough L shape here. And then the one on this side might just be them removing plastic because they had these side actions here, and you would end up with too much thickness, and you would get a sink in that area. So I think that one doesn't actually have anything to do with the operation of the tool, just with the production of the tool. So we'll do this one since it's non-critical. So all I've got to do is sketch on this face. And just to keep my datums all together, I'm going to reference it all the way from that edge so that I'm not compounding any errors. Let's go 74.5. I don't have to be super precise on this guy. And then from the outer edge, come in. This one's a little bit trickier. Really just 1.2. And then I can draw a rectangle to make the rest of the shape. And just measure the width. Let's go with 3.76. Let's call it 2.5. Even though the 45 kind of cuts into that, that's all right. Not the 45, the fillet. All right, it's 3.5 deep. I'm gonna do 3.5 times 2, so I'm symmetrically cutting it, so I cut the other chunk of the fillet away. And that accidentally cut way too deep. What the heck did that do? 3.5 times 2, so just 7. That's all it should have done. Okay. Save. And let's do the T-shank cutout on the other side. We're again going to measure from one datum, so all the way from the end of the part. Let's call it 74.4. All right, let me catch up with chat here. CFM Tools says his was good quality, and Rhododendron, I'm mispronouncing that. Personally, I'm not a huge fan of the way they store the T-shank blades. It's very awkward. It is very awkward to take them in and out. I don't know how they could have done it better. Once I kind of have one of the ways I'll show this as a way of how I design some of my other parts. So let's switch really quick to, this is a design I'm trying to come up with for the 711L T-shank, or not T-shank, the kind of T-handle kit, where they sell 2 extenders that you can convert into a T-handle. And so what I'm trying to design is a carrier that will carry an entire WIA Technician's kit, all 13 bits, along with those, and I wanted it to fit in as small of a profile as possible. And so rather than design the 3D print first, I actually designed where I want the parts to land. And so I'll show you with that how I actually do that with CAD. So let me open up a different part in my library from 711L to bit extender T-handle, and let's open the kit. So this will be a little bit of an aside. Someone's going to ask about that. Yep. Yeah, this is going to be upcoming. It is a little bit laborious to install the magnets, but we'll see how much it's going to end up costing. All right, so this is the 3D model of it. So obviously what I did is make extremely accurate 3D models of each of the tools. And then rather than design the part first, what I did was built myself a sketch. And this sketch has got a bunch of parameters and dimensions, such as basically how deep do I want the component to sit. So I want these bits, for example, to sit 2.8 millimeters into the depth of whatever the outer diameter is. That gives you just enough push that you can push the parts out without them feeling like they're protruding. Then I position the 3 components that I basically can't really move around, meaning like I'm gonna need a center piece because that's going to be the driver. I'm going to need to hold the extender, and I'm going to need to hold the right angle piece. And I set the depth of the right angle piece to be very similar, so it's just barely poking above the component. Same thing over here. Then from there, I can actually completely parametrically modify this. So if I do 36, for example, whoops, I did way too big. Mistype that. But if I did 36, it would change where these things land. Or let's say I wanted to make it a circle instead of an oval, because that might be an option. And here I can see that I'm going to start hitting, so it's going to have to be like 34 by 34. Whoops, over here, 34. And in order to, it will reposition these components. Now I'm not going to exit out of this properly because it will go through a whole big calculations and things. But what I would end up doing is modifying where those positions of all those parts are. Then, and it probably might end up breaking. Nope. Okay. And then this part is completely built and derived. So I talk about how much I love synchronous mode, but actually I did this part completely in ordered mode, simply because it's actually driven entirely off of the dimensions. So I can actually adjust that sketch in the assembly, and it will update this part dynamically, meaning it'll actually kind of move all the cutouts and things like that in order to dynamically edit this part. And so when I do an insert for this guy, I'll do the similar thing. Is instead of designing the 3D print, what I'm actually doing first is designing where are all the parts going to land in relation to each other, meaning I got to leave a certain amount of plastic between each of these components, right? I got to leave magnets to hold components into place. I want to make sure I can store this bit. So that, and that kind of sets the depth and the length. So I'm actually geometrically putting all these pieces in first, and then building the 3D print around it. And I do have the ability to make any geometry I want using SLS technology, so I'm not restricted by worrying about layer lines or anything like that. And that's how I kind of build those kind of things up. And so what I'll end up doing is, once I have the cavity size, when I can build a holder by maybe putting the T-shanks in. Maybe if you put one T-shank and another T-shank, you could put a 1/4 inch bit down the middle, a full size, or magnetically hold them on. There might be a couple options once I start playing with that. But I assume if those options were there, Leatherman would have already done it, but maybe not. All right, let's get back to the part here. So I have the depth of this. I don't have the distance from the edge. And this is, from that edge, 1.1. Whoops, I typed 1.2. Whoops, what did that, why did that, I said -90. All right, there we go. And this has a, this is, by the way, this is a trick to stop yourself from just reading a number and trying to measure a number, which is, rather than looking at the calipers while you're doing the measurement, flip them over, try to find that spot, and then kind of flip it over and see if your measurement lands on a nice round number. That'll stop you from just guesstimating and assuming it's 3.5, even if it might be something else. Now this cutaway goes all the way out, so I can just leave that all the way out. This cutaway goes over. Call 4.3. And I'm going to do the depth from the edge, because that I can measure better than I can measure 2.29 or 2.54. I'm going to guess it's 2.54, which is 0.1 inches, which is the thickness of the T-shank, I think. So that sounds more correct to me. And we'll go ahead and close that sketch off. All right, let me catch up with chat a little bit. They could have had it exposed there, but wouldn't have the risk of it being lost or dropped. Well, I don't mean yeah, I think the cap still is needed, but I think they could have done something to make it easier to pull that out. And CFM tools, this is pretty close to how to design mine, but not parametric. I need to switch to CAD that lets me do parametric models in the future. Yeah, if you're using SketchUp or something that's a polygon model or a Blender, parametric modeling is a whole different beast. Now, I will say, if you get your hands on Solid Edge, you know, I'm paying for my own license to Solid Edge, and it's not cheap. It's not much more expensive than other professional CAD programs, but it is, to me, infinitely more flexible because there isn't that rule set. Like, for example, I just drew this sketch on the wrong plane, and I'm just going to drag the sketch up to the plane I need it to be on. Try doing that in another program without completely breaking and doing 3 operations just to even do that. All right, so we'll cut this away by a depth of 3.5. All right. That gets us that geometry. So we're getting closer. And I was probably, already spent a couple hours on this. And this is a lot of time. So another reason I don't share my 3D models much is that it was a huge time investment. All right, let's figure out if we can figure out this stupid chamfer, why I can't get this done correctly. So I'm wondering if that's even a radius or if that is an ellipse at this end. Nope, it's not a radius. It is definitely an ellipse, right? Because it ain't any bigger. So that would explain why I couldn't figure it out just by doing the revolve operation. Okay. In that case, what we'll end up doing, let's assume it still stops on this center point. Actually, it doesn't, because it kind of comes over to this edge. All right, let's come in from the center here to this edge by whatever we measure here. Let's call it 15.4 to count for the radius that I'm seeing. All right, and then that's a little harder to measure. Again, I'm going to need the straight edge. I need this gap here. And I'm going to not do this in front of the camera because what I'm actually going to do is hold up and use my laptop screen as a sort of a whiteboard, as a white background. And then that way I can see the silhouette of the 2 parts easier. And then move the calipers kind of behind it, trying to stay in plane. Come on. I'm getting about 3.2. So this comes in 3.2. This is just a reference line. Whoops. Jumped off a different angle. 3.2 at -90. Okay, and I don't need this line anymore. And so now I need an arc. Like I said, I don't think it's a circle. It's actually an ellipse. That's here to here and out to there. Make sure that lands on that spot. There we go. I don't know if that's right. I don't think that's right because I don't think they would have made the rest of this an ellipse. Oh, Okay, I see what's going on. Because this piece here is a cylinder that then continues off. So because it's essentially because of this, I'm trying to explain this. Because we've got this rounded geometry combined with this curved geometry, I think what this is actually is maybe just an offset from those that ends up looking like an ellipse if you look at the entire piece, but it's actually a half circle that continues on. Is that right? I may end up doing, I'm going to do this later because what I'm going to end up doing is building this geometry. Sorry, I keep switching between camera and, but once I build this geometry back here, I will kind of derive this off of it because it's a curve that matches when that lines up and then it tapers off at an angle. Okay, won't worry about that for now then. Let's go ahead and get our pivot hole into place. That measures. Yeah, it's kind of rough getting different measurements. Let's call it 4.1. It might be an inch size too, but it's all right. And we won't worry about where these detents land because those are going to be derived off of the rest of this part, like where it wants to actually land. So we won't worry about that till we do this part. All right, I need to move on a little bit faster here. Sorry, guys. All right, let's see here. Lewis is asking if any tips for 3D modeling or design. My tips are to learn how to reverse engineer like I'm doing right here. Grab stuff, maybe not as complex as this because like I said, there's multiple compound shapes. But you know, grab something like the 711L that has all hard shapes, but trying to get these into the right place is tricky, for example. By learning how to reverse engineer, you learn how the steps you need to get something. It's kind of like drawing still life as an art class. You learn there's the object. If your painting doesn't look correct, you haven't done it correct, right? That's what a still life kind of is to a certain degree, unless you're being interpretive. So you have that as your reference. Now you copy, and that can get you started on a lot of learning the steps. If you get your hands on Solid Edge, there's a free educational version. They had a low-cost maker version too at one point, or even free. I don't know what the availability is of that, but the synchronous mode is so much more intuitive and forgiving compared to ordered mode, where you broke because you went back and edited step 5 and that broke step 15, or a plane disappeared because you accidentally deleted it and didn't notice for 10 minutes that all of a sudden a bunch of other stuff is broken. It doesn't have that. It just has the use the sketches, build up the tool, and this is still parametric. This is still a solid modeler. I can still grab this at any point in time and change the dimensions. I can grab all of this geometry and move it if I wanted to make a longer version. There's nothing that stops me from doing any of that. That's what makes it completely free while still providing a full solid thing. And Siemens, who makes the software, is the people who invented the solid engine that everybody uses. All right, let's go ahead and add the screw hole. I'll probably move this later because it's going to end up being obviously in relation to where the screw is on the metal part, but it's a simple part that I'm assuming is dead center. I guess I shouldn't assume. In fact, it's not dead center. I can see that it's off to one side. So let's first measure, try to figure out how far it is out here. Starting from this edge, coming in. Now it's always a little bit hard to figure out where the center of a circle is, but we'll work fine for that. 65.3. And we'll draw a circle. I'm going to leave it centered for now, and I'll move it in a second. 5.5. And I'm going to tell it circle's 5.5, but I'm going to make a reference line. And this is the other thing a solid edge does that's really nice is what I did is I started the line tool, I moused over my circle, giving me the center point. I moused over this line and it snaps, giving me a snap point. So I know I'm exactly at the center of that circle when I draw up. And from this edge, I'm getting 5.3. From that edge, I'm getting, yep, so it's not, it is off center. So let's give ourselves the 5.3, lock that line down, and I'm just going to say that this dot needs to be on that circle. Come on, that dot on that circle. There we go. And that just dropped the circle down for me. Didn't have to do anything weird, just had to draw and do what I want to do. All right, it's 1.8 depth. And CFM Tools is thinking about switching to Fusion. Yeah, so I haven't used Fusion. I've used a couple others. And what the heck? That was not 1.8. Why did that keep going deeper than 1.8? That's 1.8. Enter. There we go. Yeah, I haven't used Fusion. The couple of times I've tried to use, actually I tried to use it for doing, because it has good cam software, and I was trying to do the laser rifles gun stock. I did not like using it. I don't know. There's something about it that I didn't like. It felt unintuitive to me, but it might just be that I've been using this for too long. All right, next up is this kind of cutaway. Now to me, this cutaway is completely derived off of the Leatherman ratchet, which, voila, I have the Leatherman ratchet over here, right? But before I get that started, I do need to move this part because I started its model. It needs to come down 2.6. There we go. So it's sitting below the cap. And if I were the guys doing the CAD on this, there's a couple different ways you could do this, but the simplest way is going to be just to draw a side sketch. And let's grab the real part. And let's see how much tolerance they gave. Let's use the one that actually came with it so I don't use my old one. So there's not much tolerance. There's maybe half a millimeter, so 0.2 or 0.3 on each side. And then it looks like they did the cutout as big as, a little bit bigger than this guy. And then they didn't do where the neck is, so they just continued that cutout all the way down. So what I can do here is I need the center of the ratchet. I need the edge, which I need to grab a silhouette edge. And why is it not wanting to grab it? Make sure he's active. Sorry, my watch keeps grabbing my calipers every time I put my hand over it. Come on, why is it not giving me the silhouette edge? It's weird. It should be letting me project those edges from that part. Let me open this part and see if it's got some sort of weirdness going on, like I simplified it at one point. Nope, that's correct. Okay, let's get back into this guy. Let's save first. Sometimes it loses its association. No, it's there because it let me grab where the magnet was, so it's just a matter of it not grabbing that silhouette edge for some reason. And there it goes. All right. Just wasn't able to mouse over the right spot. And we're going to grab that edge, and we're going to grab this edge back here. And the geometry of the part. So we will link all these up. And we're going to offset them by 0.2 millimeters, which is what I think they did. And like I said, that's as much of the sketch as I need to get this cutaway. So what we'll do is go to Revolve, and around that is our axis, 360 degrees as a cutaway, and voila. Now it's not quite, they definitely have a little bit of rounding. Let's take a look at, so now that I have this, I got to kind of look at the actual part. I don't know if my angle here is correct, because the pen has a longer shape than I'm seeing here. So let's take a look at this from the side and see, again, holding this up to the screen. Nope, I think this guy is longer. And I think this edge is correct. Get this right. Oh, I don't know, it looks correct. I'm not sure what's going on here. This guy's actually a little, maybe a little off, but why do these look more elongated? Guess what I'm trying to show here is that if I rotate this face down, those get longer. So the way I guess the other way I could double check is the measurement. Double check the measurement of this edge. 34.8. So let's go grabbing the real part. The other way to do it is with the calipers off. So 33, which is close enough to 34.8. And I can also try to figure out where this edge ends. So let's get, come on, give me that edge. So that's 41.35 is this guy end. It's a little bit hard to see. Having to figure out where the apex is, 41.6. So it's maybe off by 5 degrees. I don't know. Let's go ahead and change it by 5. All right. And because that was beyond the edge, I don't have to cut away like any flats or anything. I think that cutaway is fine. I'll worry about the rounding later. And let's see, is there anything missing? I'm missing the pocket clip holes. And that stupid chamfer over here. And then the logo. And I'm not going to model in the actual ejection port circles that you see. But getting close to getting this guy done. So let's do the pocket clip holes. So those are going to be a little bit tricky. What I need is a tangent plane that gives me a plane that is tangent to the outside edge, since that's a curve. And again, keeping my datums together. Doesn't matter where I start. I want my distance of these to be correct. 71.7. And I am going to do the distance between these holes. And this is a trick I do with holes. You don't try to figure out where the center of the holes are. You can do it from edge to edge. And for that, I'm going to need my magnifier to actually see this. All right. I'll show in camera what I'm doing up close in a second. Now this is an old enough the pocket clip is from the Free series, and I know that the Free series, they used inches a lot more than metric, but I'm still... So what I'm doing here is measuring... Whoops, sorry, knocked the camera. My stupid headset won't stay up. Measuring the left edge to the left edge, because I can see that a lot better than I can see the middle of the holes. And I'm getting 9.6 to 9.7. I'm going to call it 9.7. And then I need to figure out kind of where they are in relation. I'm going to go ahead and come off of this edge. So from here down. Now this one I am going to try to figure out where the middle of the hole is, pretty close. Let's call it 3.5. And then I can go back over the, in relation to that hole. Come on, snap to the right spot. Or just do 9.7, there we go. And then for these, I'm actually going to use, I can actually see that they're recessed slightly, then they're tapped. So let's do the recessed hole first, and we'll do the tap inside after. So maybe 2.5. And I missed that. There we go. 2.5 on there. Now this depth is probably going to be impossible to measure. I'm measuring 0.7. I don't think they're that deep. We'll just go in 0.5, make it look visually correct. And maybe 0.6 looks a little better. And they are tapered, but won't worry about that for now. And then if they're the same as the Free series, which they said it's the K series pocket clip instead of the Free series pocket clip, but these should be 256 threaded. And I can't tell how deep they are with the calipers, but I can put in something like a tool, like that, put my fingernail down on it. And it's only 3 millimeters deep. All right. Measure the lid, measure the ID of one of the holes, and zero the ABS. And then measure the, yeah, I can do it that way. It's a little bit hard when they're that tiny. All right, so we'll make these as threaded, 256 to the hole extent, and we'll go ahead and make it tap drill diameter to a depth of only 3 millimeters, or let's call it 0.125. Let's say that you made it 1/8 of an inch. And inside that plane, on that spot, and on that spot. All right, let's take, so we can't do the detents yet. Like I said, I don't need that plane anymore. That was just a tool. I can do the rounding. Let's go ahead and do the rounding. Sometimes I do the rounding in ordered, sometimes I do it in synchronous. It doesn't matter too much. But let's figure out the radius of these by using our radius gauges. Bigger than 4. Nope. Okay, is it not a metric radius? 4 doesn't feel right. 6 feels too big. And 5 doesn't feel right. It's definitely not any bigger, not any smaller. They might have done it as 2.54 or 0.187, made it an inch size. Yeah, somewhere between 3 and 4, so let's call it, so what's 0.187 inches? 4.75. Yeah, let's call it 4.75, just as the in-between. Let's assume these are the same. Although they look smaller to me, so I'm going to do them as 3, which would be closer to 1/8 of an inch if they used inches. All right, now what we don't have is our main chamber inside, and we're still missing that stupid taper. Can I do that taper at this point? Let's go ahead and get it started, and then I can always redo it later if I need to. Give me that sketch. Attempt number 3. And measure this for the freaking 3rd time. Let's get rid of the radius gauges. Sorry, I'm using my laptop screen as a whiteboard, or as a light box. So 3.4 down. Then there's a tangent circle, and if I make this 3.4 and I make the circle concentric to there, that's still definitely not big enough. And then the circle ends, or half moon, at 15.5. So I don't think this is a shape like that, or it could be. It doesn't visually look right to me. It looks like an almost perfect half circle, so it could be an ellipse, or this circle's not concentric. So if I grab the circle and start expanding it, we get closer to a circle with these edges kind of finishing it off. So trying to look at this assembly. How they designed it and what they made this shape kind of derived off of. All right, so I want to make sure this is directly over our axis, which is currently hidden. Keep that centered. Whoops, wrong thing. Give me the circle. Give me the center of the circle, you stupid program. There we go. And show me the base. What is going on? Why is it not letting me see the base? All right, I'm going to save and see if that fixes it. It did. Okay. So I'm using the constraints here. This is a horizontal vertical constraint, meaning I want to make sure that this circle is always in line with the base. Well, it almost looks like if I did it perfectly in line with the base, that might be the way. Well, that would make it concentric to that circle. So let's drag this off center a little bit and then do that constraint. Center of the circle, constrained to there. Now really what it is where does the ratchet land when it's opened? So where is the center line of the ratchet in relation to the body? It's not the same as that circle for sure. So that's what's a little bit tricky to figure out here. Can we figure it out from what geometry we already have? Yes, because we have the pivot point and we have, okay, that's all I need to do. All right, what we have is this. We have where the ratchet lands when it's folded. Then we have the pivot point, which is this line here. So now this, second, this line is not straight. Make sure that's horizontal. If I mirror where the ratchet lands across the pivot point, that's where the center of this circle is. And now if I make this guy concentric to that guy, there we go. Got to fix a couple other pieces. That line to there, but collinear to there. There we go. So this is 15.5 wide. That's why it's a circle that isn't quite a circle. All right, finally figured this stupid shape out from which I tried to do at this very first step and failed. Had to have more pieces in place in order to make that work. Actually, all I really need is this and this. 1 second before I break everything. Why are these landing in different spots? They shouldn't be. They should be symmetrical to each other. Okay, I think I did that without breaking anything else. Okay, now this, though, does go back and taper back. So either they cut this without changing the shape at an angle, or they did a loft operation. I'm guessing they cut this back at an angle. We'll see here when I try. First, I need a reference line for where this is going to stop so I get the right angle. So from this edge, where does this shape end? Let's call it 81. And if I go over to here, I get a 111-degree angle. So it's probably 120 or something close to that. All right. Let's go ahead and extrude this with a taper as a cutaway. Let's see here. So let's leave it at 15 for now. Why is it not wanting to cut away? Let's try this one more time. I think it's actually doing the wrong operation, even though I told it to cut. There we go. Let's try 20 degrees. 20 degrees gets us much closer to what it looks like. And I can delete these and see if just leaving it as a round. So what I'm looking at here is how does this shape kind of terminate? Sorry, bad focus. It does. This is really going to be hard to see unless you've got a trained eye, but this line is going straight and then kind of curves off, like it starts to curve off that way at the end. This one kind of goes straighter, but I think there might be a hair chamfer or something else going on over there. So if it goes straight, then these wouldn't be there, or if it has that curve, it kind of helps if I remove those. I think to me it's one shape without the extra bits. Save. All right, that is 3 hours, or sorry, 2 hours and 20 minutes to model just this one part. Again, we don't have the detents, we won't worry about those yet. I pretty much can guess where they are. They're at 45 degrees, obviously. But actually, no, we can do it because I see that they're derived from an endpoint. Let's go ahead and do them then. So you can see, come on camera. and pull out my pointer. This flat continues in, and then this cuts up. This one, I think they kept that flat in the cut and they just rotated it 45 degrees. So let's see if we can duplicate that. So we're going to come in, and it's going to be hard to determine the depth of this. There's another way I can do it, which is measure the finish thickness to the other side, which comes out to 11.06. Considering there's a little bit of a round there, let's call it 11. And what are you doing, CAD software? 11. So it's a cutaway like that, and then what looks like a 45-degree angle, maybe more. That looks like it's more. And there's going to be a little bit of a round in there. Something like that. So I can take this cutaway like this, subtract it. Now I can grab all three of these faces and rotate them 90 degrees. And then again, whoops, didn't mean to grab the inside of the circle. And grab them another 90 degrees. I think that's what this kind of ends up looking like in the end. All right, won't worry about any of the like decorative rounding or any of the other pieces later. There's a little bit of a round. In fact, we can do this in ordered. That way, if we have to change anything, we can do it in synchronous mode and then just have it apply these rounds. So what we're going to do is, there's a very small round that doesn't continue into this part. Along these edges. And it looks like they tried to put it on these edges, but like comes out dirtier back here. But that's just the seam line from the side operations. But we'll make it look a little more correct. All right. Now we can actually do the interior, now that I'm thinking about it. So how do we think the interior is built? It's going to be, and let's get into a cutaway mode so we can see this live. So I'll go to sketch plane so we can see a cutaway view. So earlier I said there was a little dip up in the middle. They probably did that with a thickening operation. So this comes in here and then has some sort of lip. This is going to be a little bit hard to figure out without something like a mold. But because the plastic has to be consistent thickness, some of it's going to be derived off of the existing parts. All right. What we can do is say maybe this edge and this edge, what's our thickness of plastic? 1.5, I think. So for keeping consistent thickness of plastic, that should be 1.5 from that edge. Whoops, wrong edge. This is the bump up inside. But it can't bump back down because in order to bump back down, it would have to, you can't have a negative space for an injection side action like that. And there are the mounting holes too. And we have this piece here where the T-shank is. So that has to come up 1.5 from there also. So this is going to be sort of guessing. It looks like to me, what I can see inside, that this is kind of an even piece in like that. This bump out definitely is still there. Come on, what is it? It's snapping to really weird crap right now. Just jumping all over the place. There, right there. Stay there. This isn't quite right. This is going to be the cutaway profile, but not quite what I need the final shape to look like without being a revolve operation for the whole thing. Is a little bit tricky. I could use a thin wall tool. I mean, it is circular. It's mostly circular. In which case, we'll revolve this section. Come on, what is it? Give me the region. Come on, there it goes. Revolve this around that axis. But that's going to cut away a bunch of other crap in the front. So here's the alternative. What we're going to do is build another tool. So we'll add a body. Did it actually do it? Yeah, okay. And we're essentially going to make the same tool that they use in the plastic mold. 360 degree. However, what we want to do is I'm going to hide the tool body for now. And we're going to thicken. I'm going to add another body. I'm going to thicken these faces up by the 1.5. And we'll grab our tool body. Come on, software. Why are you... What the hell? It's like it won't let me click on the left side of my screen. Something's weird's going on here. It's like either about to crash. There it goes. Or it's just being slow. All right, let's turn off the side view. We will go ahead and thicken this up so it actually cuts these sections away. Take this and subtract that. Grab this whole face, bring it in. And they might leave that just like that because they do have to leave some plastic behind there that can't be super duper thick. Let's get rid of these sketches, they're just distracting. So that's close, but I think there's more than one shape inside, like more than one bump up. It's almost like it tapers in. Well, it does. It has to go because it has to go thick or thinner essentially because it has to get beyond where this is. So that has to come up 1.5. And it looks flat to me. So let's say it starts here. Actually, it didn't start there. Kind of bumps up for a bit. Where is it? Here. It kind of comes up like this. And really, I won't be able to tell if I get this anywhere near close unless I try to make something that fits in there perfectly and then find out it jams at one spot or another. Okay. Oops, I don't want that cut like that. Needs to be here, and it needs to clear that. This is just random at this point. Randomly guessing what that looks like on the inside. There are materials out there that you can basically, like, it's like a Play-Doh, you can kind of jam into an opening, and then it will form into a hard substance that doesn't shrink. And then you can basically pull that out, and then you can like 3D scan or measure that. We're going to save that tool off as a construction body. All right. Long way to get to something that looks like this on the inside. That doesn't look quite right to what I'm seeing through the flashlight. I think this is a little thinner, or it's a slightly different angle. Let's go from here and rotate this. Give me the rotation point. Come on. Obviously can't be so thin that it cuts all the way through. Yeah, so maybe that the angle's right, but it might be that it's revolved. But it doesn't look like it in real life. It looks like a couple of flats, and in fact there might be a third flat inside there. Yeah, it's going to be tricky to figure out later. All right. There's no hard flat spots where I can just drop the calipers in there and get it figured out. We'll leave that for now. Okay. Technically 3.5 hours just to do this part. And we'll switch off now to the 3D printed titanium piece. That's going to be a little bit tricky to figure out just the same, but a lot of it's derived off of all the geometry we just built. Now, one thing that I think several people have noticed is that the ratchet is twisted by an angle inside. I'm curious why they did that. Because the set screw is straight. Oh, there goes another hour. Alexa, turn on the workshop light. So I can tell that that is straight, which means that even though they twisted this, they didn't actually do the screw in a twisted manner. Did they do that so that when you tighten the set screw, instead of it pushing down, it would actually twist slightly? Like it would, because it's off center. I'm guessing they did that so that when you tighten that set screw, he gets locked in really tight. Instead of if you tighten it off axis, there's less likely for this to start pivoting around because there isn't a center pivot point. That's my only guess for why they canted that. There might be some other reason why they decided to twist it, but don't know. All right, let's get to constructing this part. For this one, I think we're going to put the axis straight on the pivot. So we're going to create a part in place and metric again. .009 titanium. Why did you make it inches? Software is lagging. Reset the file units. Oh no, it did make it metric. Just was lagging and said one thing and did another thing. All right. I'm actually going to close this so that I can move the pivot. Move it to the pivot point. I guess what I could do, since I'm going to derive things, is try to figure out what that twist angle is. It's twisted slightly. in this direction. And I can't really tell the angle here. In X-ray mode, I can kind of visually look at it. And try to compare it to the screen to what I see in reality. I'm guessing 10 degrees. It's not 15. It's just a weird angle. There must have been some reason they had to do that. All right, let's start building the titanium body a little bit at a time. Now a lot of it, this will hopefully go faster because a lot of it's going to be derived off of features we already have. So what I'm going to actually do is, starting on, come on, this face. I don't need the reference planes, they just get in my way. Measure the hole diameter, 4.2. And then does the outer diameter of this match? It does. So we can just derive that. Now what I want to do is move the sketch to be in plane with this. Again, incredible things that this software can do because I didn't have to bring anything over. I just literally had to drag it and reference the assembly I already have open. All right, this is a cylinder that pops up. We'll end up cutting away later, but for now it has a thickness of at least 6. Interesting, that's measures 6, but doesn't look visually correct. Trying to look at this from the side and see if I'm missing some other geometry. I sort of think, let's look at the straight edge. Yeah, there's a drop off for some reason. About 1 millimeter. That just goes off like that, but for now, we won't worry about it. Physically measuring at least 6.3. Let's call it 6.35. Let's assume they made it a 1/4 inch thick. And then we can drag the same piece, the same sketch down to this side. And it has a maximum thickness of 2.7. All right. Rodogen is asking, how exactly do they 3D print titanium since it oxidizes in contact with air? Well, they print it under nitrogen atmosphere, first of all. In fact, most powder diffusion, other than my Fuse 1 over here, print under nitrogen. Like the bigger new Fuse X1 requires nitrogen, or if I want to do different materials like nylon 11 or glass filled or carbon fiber, I have to do nitrogen for these machines. So yeah, you stop it from oxidizing by printing it under a nitrogen atmosphere. Okay, this guy is funky. So we know where our detent is because we have that geometry already. And the detent's got a certain amount of thickness here. That's going to kind of set up some of the rest of the shapes here. I'm trying to figure out which shape I want to do next. I can either do the ratchet, let's do the ratchet shapes and the rest of them. Well, actually, so let me think about this for a second. Yeah, I can do the ratchet shape for now. It starts off equal, but it looks like it gets a little thicker, but that might be an optical illusion. It might be just one body. I think it's an optical illusion because what I'm looking at is this reflection where this line. So let me see if I get some more light on it so I can show. One of the ways you can kind of see if something is, I'm trying to figure out if this goes straight and then tapers off at the end. And if it does, it's only due to processing because the reflection line is very straight. It doesn't suddenly taper off at the end. So I think this is actually a straight part. We're going to do a couple things. We're going to start at the other end though. So I'm going to give myself a plane, and I'm actually going to move it first to the edge of the pivot. Then I'm going to move it by whatever I measure here, which is 42.6. Try the other side without pivoting the part. Now I'm getting 41.3, or I can move it until a part clears going through. So let's say it's 42. The answer to life, the universe, and everything. All right. And then starting on that plane, a new sketch that will be concentric with the Leatherman ratchet. And fortunately it's got that taper at the same time. So I'm gonna have to like flip this around in CAD and work it from the other side. For now, that feels like 16. I didn't make it so the ratchet goes all the way in. Which actually I find interesting. I thought they would use this face as a stop instead of the other interior face, but they use the interior face as a stop. All right. The other thing I can do is just copy this part so I can work on it in two different orientations. So I rotate it 180 degrees and work on it from this side. And because we want this to line up with this circle, I have to save first for it to get the references updated. Come on. Why are you not highlighting that one? There we go. So are these guys concentric? They are. Good. That's what they should be. All right. Need to look at the correct part. So this guy kind of comes out, and this is, again, we're looking at reflections can really help. I'm trying to figure out if these are curves or flats. And they're curves because the reflection moves in a curve essentially. So we will grab the curves we made earlier that make up the outside edge. Well, I can mirror this afterwards. And so what I want to do is a curve off of this. That curve needs to be concentric to that curve without moving the circle. And without moving that curve. There, that'll make it offset but concentric. Mirror this to the other side. And there's a couple things I can do. Even before I get started on the rest of this, I can grab this face, subtract it, deleting the chunks over here. Which, let's go ahead and make that guy fully round. There we go. And then the other really odd thing I'm seeing here is that that flat is not flat. It is canted. Or is it? No. That stupid inside piece screwed up my brain. That is a flat relative to the rest of this. And it should be interesting. I just noticed that. There's a cool part. Those guys are equal to each other. So I can derive that off of what I already got. So let's start with a real basic shape This can come straight across, and we'll worry about the thickness of it later. And we're not going to join these up with each other quite yet. I just want this basic shape. And I'm going to switch back over to the other orientation. And let's make these parts, let's make this guy orange, just so I can separate it visually when I'm in assembly mode. And so this face should be coplanar to this face. That's what I mean by everything's kind of derived off of the existing assembly, instead of trying to model each one in a vacuum. And then this guy is, we actually derived this shape off of the other shape by 0.2 millimeters, so let's just do the same thing here. Or I can grab that silhouette edge. It's gonna let me grab it. Come on. There it goes. That edge. And I need the center of this point. Those are all the lines I need to get the job done, which is this along that axis, cut away on that side by 360 degrees. And there's our kind of interior cutaway. And then there's these little chamfers on these corners, and that's probably because they saw this exact same thing and cut those away. I'll do that later. For now, this will work. I actually kind of need those flats. Well, actually, no, I can drive this next operation off of the part. All right, sorry. I'm trying to explain a little bit more what I'm doing. So I actually need this face and this face. And this is what they use as the hard stop. So, oh, well, actually, let me think about this. Something's wrong because, like I said, there's a gap here between these two, and I don't have that gap. But I have the ratchet way at the end here. And I measured this part. So why is there no gap? There should be a gap here. Let's measure with it in assembled mode. Oh, something's going on. Is it not docking fully? Because I can't close it up properly. Oh, don't tell me that they changed the ratchet. Those are different, the divots at the end. Okay, I think this is my old ratchet because it's smooth, and this is the new one because it's pushed out. Okay, gotta be careful mixing old and new ones. Oh, interesting. This guy goes all the way in, and this one doesn't. They did change the ratchet. So they must have changed the diameter of something down here. 9.45. 9.52, that's not much difference. But 9.4 versus 9.5? They changed that by 0.1 millimeter? That's like, is that all the difference it's going to take to make that go all the way in? Yeah, so that's 9.5. With roughness inside there. Sorry, I'm not holding the camera right. Interesting, they shrunk the diameter to 9.4. Okay then, that explains why mine did not dock all the way. The old one. Okay, so now I can get back to editing this, and it should dock completely, which is where it is right now. But starting from this edge here, or I guess we got our center line. Right. Come on. Have to constantly switch. So let's make this the 9.5, which is how it would be if there's zero tolerance. Wonder why they did that. Mysteries of Leatherman. All right. Don't need all that. Revolve. Around there. There we go. Save. And then next feature is, so I'm curious how they did these cutaways. They almost look like they just took a virtual line and revolved it. And there's also a little dip here, which is what shows up here, because that's kind of an apparent derived piece. Yeah, this piece might have to be finished another day. Let me think here. Let me try to get the major geometry done at least. And then I think for the internals, I'll do that another day, because it's already getting to 3 hours. All right. Actually, should have made this guy a separate body. Let's do that now. So what I can do is add a body, grab this part, copy it off by like 10 or whatever, 20. Now I have 2 bodies, and I can delete all of this chunk from one and all of this chunk from the other. That way these guys aren't going to merge until I want them to merge, because there's going to be lots of geometry I'm going to have to keep adding and subtracting from these. Okay, so this, well, actually this face is again derived geometry, so it is from, it has to come up and hit flat to the handle. Yep. And then there's the cutout that makes the detent feature. There's the cutout that makes the T-shank feature. And a couple small cutouts for the pivot screws, but I won't worry about those yet. All right, there is a little bridge here, cutout for the T-shank. There's actually an undercut for the T-shank. This is something that wasn't immediately apparent to me when you dock the T-shank into here, that you got to actually put it in one way. You put it in this way first, it doesn't go in there correctly. And that undercut is like one of the things that makes this so you can 3D print this. You can't do that kind of undercut with any sort of injection mold, not without some really weird side actions. All right, let's take a look at this part real quick, because I think it's a couple parts merged together in order to get this working. For the T-shank cutout, I can actually derive some of that off of the T-shank cutout we have in the part. All right. Well, you know what? At 3 hours, I think I'm going to call it here. This is getting enough of the geometry that you could start designing some accessories around it. I can do the pens later. Those are simple. They're all derived off of this. The pivot screws. This gets the major external geometry, but I need to get some food in me. And 3 hours of standing's already been enough. So I think I'll do some more of this. I might, if I work on this more, I'll be on my Discord on the voice channel, and I'll kind of stream it there instead of YouTube. So thank you to everybody who's watched. Appreciate it. And if you catch us later, you can always join Discord if you got questions or any curious about Solid Edge or the different 3D models and the garage number 9. But yeah, I got to call this at 3 hours.